7. Bacteria. The growth of a certain bacteria can be modeled by the logistic growth function shown there, where t represents time in hours. Estimate the limit of b as t approaches infinity, if it exists, and interpret your results. So let's first go graph this and see what this graph is going to look like. So we have b of, we can call it t, we can call it x, but I'll just go ahead and copy it exactly as they have it listed. B of t equals 675 over 1 plus 135e to the power of negative 0.6t. So there's our function. As long as you start with b of t, you need to use the variable t as your independent variable there. And we have our graph. I'm going to zoom out a little bit so you can just see what this graph looks like. Oh, wow, there's a trick to it. This is the logistic function. It has, I don't know how to describe it. It's kind of like a mountain ridge, and that's very common for the logistic function. So there it is. There's our picture, and I will screen capture this for us so that I can copy it over here. And let me shrink this because this is just huge. All right. So now that I got this back normal, what we could say is this limit, as we go off the graph to the right, if we look, you can see it's getting really, really flat. And what number is it getting really, really flat on? The answer is, if you look at the y values, they're not changing there. It's 675. And I guess I could have shown you, it might have been helpful to show you a table here. If I start typing in some large x values, let's just go 100, let's go 1,000, let's go 1,000,000. You can see that it's approaching 675. So that'd probably be even a better table to show you here. We can now state with confidence that the limit of b of t as x approach, or rather t, not x, as t approaches infinity would equal 675. And what does this mean? This means if you're trying to interpret, what this means is the number of bacteria approach 675 as time increases without bound. You could say as it approaches infinity, but I'll just say without bound. As time goes on and on, the number of bacteria approach 675. So now here on part B, it says the population of a certain city is given by this function here. So P of t is going to equal 0.7 times 1.1 raised to the power of t. I'm going to turn this one off. Where time is in years. Estimate the limit if it exists and interpret your results. Now remember the last one we needed to zoom out to get that table. So I'm going to kind of do the same thing here. I'll do 30, 40, 50, 100, 1,000, 1,000,000. You can see it's not the same value this time. So as I zoom out, you'll notice this graph happens to be different. And let me go ahead and throw that one on there so you can see the difference between these two graphs. It's all right. You go a little bit lower so I can get the rest of that table one more time. There we go. So now let me shrink this. Okay, so this limit does not exist. The limit of p of t as t approaches infinity does not exist. Since, actually, I'm sorry. The limit we would say exists is just it goes up to positive infinity. Since we're doing just one-sided, we could say as we go to the right forever, this graph also goes up forever. So this one approaches infinity. This means the population increases without bound. As the time increases without bound. Come back so you can see that a little bit larger. There you go. And now here's one for you to try.